All right, welcome everybody to iMediSync's Unlocking HRV, a deep dive into heart rate variability and interpretation. And we're so grateful to have you here for the next hour with us and also share our appreciation for Santiago Brand and presenting. A brief introduction, we have our team for iMediSync North America. Top photo left to right, we have Cody Newman, Chris Che, Carlos Chinchilla, and myself, Rebecca Walker. We are always available to answer questions, give demonstrations, and review different reports that we have available. On the bottom, we have a picture of our MD turned CEO, Dr. Kong, our head of research and development, Dr. Kim, and ours truly, Dave Burkus, our CFO for North America. A little introduction for those that are unfamiliar with iMediSync. We are an AI-driven mental health care platform. We utilize EEG measurement technology, and as you'll hear in this talk, we also integrate HRV analysis with red light therapy and offering a preventative monitoring and evidence-based care. And as you see here, this is a picture of our iSync Wave device. It's a 19-channel dry electrode scanner, EEG scanner. It also has 19 amplifiers built in where we can collect and analyze the brain within 10 minutes. So your report is generated processed on a cloud and then given back out within 10 minutes. We also have our software side, which is the iSync Brain, which has age and sex match database, which is significant because most just base it off of age. And we offer AI denoising for independent component analysis, as well as AI features for biomarkers for such as dementia. And we have a comprehensive quantitative reports for the clinician and easy to understand reports for the client as well. So today's webinar is on HRV analysis, but we cover a broad range of topics from mental health, peak performance, medical field uses, and my recent favorite is pediatrics. We just came out with a new pediatric report. You're one of the first to hear about it, and it assesses the brain age of children 20 years and under. Again, we're a social bunch. We'd love to get to know you, hear what you're doing in the field of neuroscience, and also please schedule a demo where we can have a more personal conversation to answer questions and see where we could collaborate and be a good fit. So just some housekeeping here. Next month, we have a presentation by Dr. Michael Rathbone. He's a neurologist, and he is going to present on concussions. In May, we're presenting at AAPB with Dr. Sherry Johansson and myself. And then June, we have Dr. Linda Thompson presenting on ADHD, autism, and red light therapy. Linda Thompson, I like to call the queen of EEG. So we are very excited for this list of presenters that will be coming. And anytime you want to see what events we have, please join us on imedisyncamerica's.com/events. And just when you thought that was it, we have one more. Tomorrow, Dr. Kim, head of our research and development, is actually presenting on real-time changes and intervention effects of QEEG-guided pulsed transcranial photobiomodulation. So basically measuring how near-infrared light therapy influences the EEG results. And I will put a link in the comments for anyone who wants to attend. It's tomorrow at noon Eastern time. And finally, we have our presentation, which is going to be conducted by Santiago Brand. And we're so grateful for his willingness to help educate us to take a deeper dive into reading our HRV reports that iMediSync offers. And Santiago, I will turn the time over to you.
Thank you, Rebecca. Thank you very much. Well, hello, everyone. I'm very, very happy to be here today sharing this information with you. I want to thank Rebecca again, Carlos, Cody, the iMedicine Americas team, as well as the team in Korea. I've had the iSync way for about 2 years now. I was initially going to meet the guys in San Diego at the AAPB conference when COVID hit and everything went sideways. So by happenstance, I ended up moving to Singapore a year later, and I flew to Korea to meet up with the team, and I had the chance to test the device, and my wife had a chance to test the device. We absolutely loved it and ended up getting it, and I love all the features that it provides. I really think that the company is revolutionizing neuroscience and brain science, and I'm happy to be part of the scientific advisory team, as well as sharing the updates with in terms of the hardware and the software, and very excited about what the future holds. My name is Santiago Brand, and I am the founder of MindLab Neuroscience Consulting in Singapore. I've been living in Singapore for 3 years now. I have been working in the field of neurofeedback and biofeedback for 16 years, same as heart rate variability. And I've been working with EEG, EEG for about 11, 12 years now. I've had the good fortune of had great mentors in the field like John Anderson, Linda Walker, Linda Thompson, and the one and only Jay Gunkelman. He's been my mentor and friend for over 10 years now, and I'm very privileged to have learned everything, or essentially everything I know about the EEG. I learned from him, as well as obviously these other mentors. So today I'm very excited to be able to explain a little bit of what HRV is and why you want to read the HRV reports that the software and the portal provides. I see that some of you have worked with HRV before, some of you may have not. And the question you're probably asking yourselves is, why on earth would I want to work with HRV? I'm interested in the EEG. I want to do neurofeedback. I want to learn more about biomodulation and biomarkers. Why do I want to learn about HRV? Well, I'm here today to hopefully answer some of those questions and more. And I want to show why HRV is important, not only for assessments, but also for interventions, and how HRV can be powerful when it comes to working with the brain as well. So before I start sharing the info on the reports, I would like to talk about a couple of aspects about HRV that I find important. The first one is the neuroanatomy of it. It turns out that the heart and the brain are linked via the vagus nerve, and that 95% of the information is afferent, meaning 95% of the information goes from the heart into the brain. And when I really read that really changed every conception I had about neuroscience. And at that point, I learned that the heart is a very important organ when it comes to working on brain health as well. Meaning that you can influence the brain even before you work with the brain by engaging in coherent breathing and optimizing heart coherence. You can influence brain coherence. And when I learned that, I started implementing this, and it really transformed the way I was doing neurofeedback and the way I was getting results with my clients. Some of the clients who were not previously understanding how the neurofeedback works, or were a little resistant to the neurofeedback, were changing their mindset and their behavior and their emotions when we started working with HRV first. And as a matter of fact, every time I go teach anywhere where faith finds me, I always tell people that I always start with HRV before I start with neurofeedback. Every client that I see, irrespective of their age and their condition, they always learn heart rate variability biofeedback before they go into the neurofeedback, without any exceptions. And my suggestion to you as clinicians and researchers is that you work with your clients and your individuals with HRV first. And once you get them to really learn it and implement it, you're going to see the difference it makes when it comes to brain activity and brain health. Having said that, Let's go back to the neuroanatomy. The heart and brain are connected via the vagus nerve, and the vagus nerve will innervate several brain areas that you can target, that you can change, that you can modulate, that you can optimize through heart rate variability biofeedback. Therefore, you do not only want to learn what SDNN means, what RMSSD means, what interbeat intervals mean. You want to learn how the activity of the heart modulates the activity of the brain and how you can integrate both for assessments, for research, and obviously for clinical interventions. Now, the first point that the vagus nerve will innervate in the brain is the brain stem. And in the brain stem, we have a structure called the medulla. In the medulla, we have some structures called chemoreceptors. And the chemoreceptors will respond to changes in carbon dioxide. Every time we breathe, as I inhale and as I breathe out, I'm exchanging two gases. I'm bringing in oxygen and I'm expelling CO2, okay? And the chemoreceptors in the medulla are going to respond to the drop in the CO2, which means that for breathing purposes, CO2 is a little bit more important. In what sense? For survival purposes, we need the oxygen. So we want to get in as much oxygen as we can into our system to nourish cells and tissue and organs and blood and everything else. But when it comes to triggering the brain for the need to breathe another cycle, the CO2 is more important. Every time you finish exhaling, the chemoreceptors are going to detect the drops in the CO2 and you're going to get signal to breathe in again. And obviously this is an automatic process. This is part of the autonomous nervous system. You're not consciously breathing unless you're training about inhaling and exhaling. Now, what's important about the chemoreceptors is that they can be programmable. They can be programmed, okay? And that means that you can change your breathing to optimize your health. On average, an adult worldwide will do 15 breaths per minute or more. That's the average breathing rate for adults around the world, irrespective of where you come from or where you are. That means that at 15 breaths per minute or more, most adults around the world are activating their sympathetic nervous system, the fight or flight. And that's the reason why people are stressed and highly anxious and worried and depressed at baseline. That's the reason many people come to you for a QEEG and you find biomarkers for anxiety, for stress, for trauma, for depression, et cetera, et cetera. But if you measure the HRV, you're going to find that their heart rhythmicity is highly dysregulated. So if the heart is dysregulated, the brain is dysregulated. And that means that we have to train to lower that. The ideal breathing rate for an adult at rest is 5 to 7 breaths per minute, a minimum of 5 to a maximum of 7 breaths per minute. And that's what we call the resonant frequency. The resonant frequency is a person's ideal breathing rate. Just like you have an ideal weight, an ideal BMI, an ideal beta amplitude, an ideal alpha amplitude, you have an ideal breathing rate, which is your resonant frequency. And that goes between 5 to 7 breaths per minute. Once you find the resonant frequency for the individual, you can train it. And the chemoreceptors in the medulla will respond to that. That means that if when you started the process, you were doing, let's say, 20 breaths per minute on average, as you learn to breathe slower, the next time you're breathing at 20 or more, your chemoreceptors are going to tell you, look, now you have learned to breathe properly. Let's do it. You will have the ability to consciously differentiate the before and the after. And that's one of the main points of heart rate variability biofeedback, is to teach people to discern the difference as to where they were before and where they are now. They can learn that they don't have to go back to their previous state, that they can operate in a new state. So the chemoreceptors are important for that. And then from the chemoreceptors, we're going to move into the hippocampus. The hippocampus is another area innervated by the vagus nerve. And this is a very important region of the brain for several reasons. First is the house of memory. So most of our memory originates in the hippocampus. It's the maker of theta brainwaves in the brain, and theta brainwaves are associated with short-term memory and longer-term memory. It's also where neurogenesis takes place, is where our brain makes new neurons that sprout and travel to other areas of the brain. So it's the birth of neurogenesis. And therefore, if our heart rhythmicity is dysregulated and we're experiencing stress, duress, trauma, chronic illness, the hippocampus is going to pay the price. If your experience has been anything like mine, when you have clients who are highly stressed, or they have trauma, PTSD, or they're anxious, the first thing that they complain about is poor memory. And that's because as we get stressed, we're going to secrete two key hormones, one being adrenaline and the other one being cortisol. Those two hormones are going to go through the bloodstream. They're going to go through the blood-brain barrier, and they're going to bind to receptors in the hippocampus. So adrenaline and cortisol, when unhealthy, when in chronic levels, are going to destroy neurons, are going to kill neurons. But they're not only going to destroy the neurons that are already being born and existing, they're going to keep your brain from making new neurons. And that's why highly stressed people and anxious people and depressed people suffer from memory. That's the first complaint you get. It's either sleep or memory or both. Now, the good news is that there's a balance, right? And so when we look at the hippocampus, with heart rate variability training, you can get the brain to do the opposite. As we learn to self-regulate, there's another substance that's secreted in the hippocampus called BDNF, which stands for brain-derived neurotrophic factor. It's a growth factor that fosters neurogenesis. The main way we can produce, or we can help the brain produce BDNF, is through movement, more specifically exercise. So as we exercise, the brain secretes BDNF, and that's why I'm a big believer in exercise. When I was working with clients, I would get them to exercise to foster and strengthen the gains that they would get from neurofeedback. But the main element is brain-derived neurotrophic factor, BDNF. And there's another type of factor that we can help secrete, which is GDNF, glia-derived neurotrophic factor. Our glia cells make their own growth factor, which fosters this neuroplasticity and this resilience in the brain. And having said that, BDNF helps foster neurogenesis, helps create new neurons, and it neutralizes cortisol. That's why exercise is the best medicine against anxiety and depression, or it's part of the intervention. So I suggest that if your clients are doing neurofeedback, that you encourage them as much as you can, and you do anything you can to get them to exercise. Because when they exercise, they're getting the BDNF, and you can actually create new neurons and neutralize cortisol. Now, there's been some recent research that shows that heart rate variability helps prevent and remove the protein aggregation that is related to disease like Parkinson, Alzheimer's, and frontotemporal dementia. So neurodegenerative conditions can be prevented ahead of time if people eat well, if they exercise, if they sleep well, and if they do heart rate variability biofeedback. And HRV, it's also been recently demonstrated to trigger the secretion of BDNF in the brain. So if for no other reason than that one, you need to get your clients HRV biofeedback to protect their hippocampus. We have the medulla with the chemoreceptors, we have the hippocampus, and then we travel to the amygdala into the limbic system. And the amygdala is one of the regions that gets most negatively impacted by a dysregulated heart rhythmicity. So you've probably heard of the amygdala hijacking, And that means that if you're, again, stressed out and depressed and anxious and not sleeping well, and if you have experienced trauma, your amygdala is going to be hyperactivated or overactivated. The amygdala links to our prefrontal cortex and the frontal cortex. Okay. And so once the amygdala is heightened, you're operating in a reactive mode. Okay. You're in autopilot, which means you are reacting instinctively instead of rationally. That means if you're angry and somebody triggers you, you lose all senses. The next thing you know, you're choking somebody and you don't know when you did that. You're reacting violently, and you're reacting, abruptly. When we do heart rate variability and we get a coherent heart rhythmicity, and we get the brain and the heart to be friends again, you're cooling down the amygdala and you're getting more blood flow into your prefrontal cortex and your frontal cortex. And then is when you can think clearly. You can slow down and you can say, hey, I no longer have to get angry. I no longer have to get violent. I no longer have to insult somebody. I can just relax. I can be under control of my own emotions. I can mitigate this, and I don't have to be going into that place anymore. So it's of benefit because the HRV approach is a bottom-up approach, and the top-down approach is the photobiomodulation, the neurofeedback, the TDCS, the TMS. Anything we use for neuromodulation is a top-down approach, and the bottom-up approach would be heart rate variability. So you're really flanking the problem from two angles, or from two different vantage points, and that's a great advantage to have against mental illness. Now, as I said that, again, you get more blood flow into your prefrontal cortex, your insula and your amygdala calm down, and you go, oh, so this is what it feels like to be calm. And I've had clients express it that way. This is what it feels like to be calm. This is what it feels like to be at peace. This is what it feels like, et cetera, et cetera. And obviously, then we go into the neocortex, where our higher order processing takes place. And again, if your heart rhythmicity is dysregulated, the rhythmicity and the coherence in neocortex will be dysregulated. Your thinking is not clear, your feelings are out of place, you're not sleeping well, you're feeling angry most of the time, you have no energy, you don't have interest in doing things anymore. Some people start contemplating hurting themselves, and the list goes on and on. So these are the different brain regions that we can impact through heart rate variability. Now, a very simple thing that you can do is record HRV and EEG at the same time, which is something that you can do with the iMedisync, with the iSync wave. As you're recording, you can turn on the PPG and the EEG at the same time. And you can actually see the activity of the heart, which helps you further understand, the activity of the brain. Now, having said that and getting some basics, let's take a look at what the reports show. And to do that, I'm just going to share my screen here. But if at any point you cannot see my screen, please do let me know. Now, you record, you use the iSync wave, and you get very nice reports. You get all these pretty topographies, and you run it through the database, and you get different things. But the thing we're talking about today, what concerns us this afternoon, is the heart rate variability. And I'm going to show you a recording that I did of myself roughly a month ago, when I was undergoing some stress. So I'll put you into context with the situation so you can understand how to read this. Now, the first thing you're going to see is the individual analysis. You have recorded, you go into the portal, you go into the section for the HRV individual analysis, and this is what you would get. Initially, you get two types of graphs, one that says the time series and the other one the trended time series. Essentially, they're the same, except one is removing artifacts, just like you would get the EEG with the raw EEG, and then the blue EEG, which is the de-artifacted EEG that they run through the AI. It's essentially the same thing you're doing here, and you are looking at some specific activity. I'm going to slow down here. Please write your questions at the end. Ask as many times as you need. Hopefully, I can answer all those questions for you. Now, what you see here is a wave going up and down. Okay, and here we have an amplitude and a spectral distribution, and then we have time over here. So this is 3 minutes and 30 seconds, 3.5 minutes of eyes open recording. This is my eyes open HRV. And the line that goes up and down is called the pulse wave. So this is the pulse of the heart. It means it's the heartbeat. That's the thumb of the heart going up and down. Now, if you notice, it's different from the EKG that has the QRX complex. So this is the pulse data, but we can extrapolate lots of useful information from these graphs. And this is mediated by the person's breathing. If you notice, as I go up, this, it looks like a Pac-Man here. There's a drop and then up again and then drops, and the lines don't look smooth. Okay, here they do, but they don't look smooth all the way throughout the recording. And that is because this is the pulse as mediated by the breath. This looks like this because this is a baseline recording. When we work with heart rate variability, we're going to be concerned with the data from two perspectives, one at baseline and then during training. I'm going to talk about both. But essentially, you get the pulse, so, heartbeat, 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 heartbeat. And the RR is concerned with the top of each cycle here. This is the top of the heartbeat. So this is one heartbeat, and then another one, and then another one, and then another one, and then another one. And the RR is the top. In the EKG, this would be the QRS complex, the Q down here, the R, and the S. Now, word of caution here, in some literature, they also call it the N or the P. So if you don't use this system, but you use another system, they would call it the N to N or the P to P or the R to R. So R, R, P, P, and N is exactly the same thing. It's just a different way of saying it. Now, we're going to be concerned with the RR and the NN because we're going to talk about the SDNN. And the RR essentially is the time that elapses between one heartbeat and the next. So it's the time that elapses between this point here and this point here. We're concerned with the space between heartbeats. And that's called the IBI, or the interbeat interval. That's the first element we are going to be talking about as it pertains to the physiology of HRV. It's the IBI, the interbeat interval. And what we want is for, number one, the space in between heartbeats to be greater and also be more variable over time. What's the unit of measure? It's milliseconds. Okay, so this is milliseconds here, and milliseconds here. And what you want is for that time to be different over time. In an unhealthy client, once you take all the IBIs and measure them, if they're very close in time or there's not a lot of great variability, you need to send that client to the cardiologist because that's not a healthy heart. For example, this is here 115 milliseconds and 110 milliseconds and 130 milliseconds and 90 milliseconds and 110 milliseconds again. That's not great variability. They're very close to each other and they're very close in time and proximity. Therefore, you may want to say to this client, I'm noticing things here. I'm not a medical doctor, but I know a few things that are that I would think it's a good idea for you to go see a cardiologist, maybe get an EKG and talk to your doctor about it. Okay. I've been able to refer people to the cardiologist, and they find arrhythmias and all sorts of cardiac conditions that you can sort of discern without necessarily being a doctor. Now, you're not diagnosing, you're not working beyond the scope of your practice. You're saying, I'm trained to somewhat identify this, and I want you to go talk to your doctor. So IBIs are important. That's the name, heart rate variability, because the variability is in the rhythmicity of the heart. Can your heart rate dance to the music? You always think that. Is my heart dancing to the music? If not, you don't have good heart rate variability. If you do, then you have strong heart rate variability. And again, we want the number one, the distance to be greater and the time interval to be quite variable. The more variable and the more distant to a degree, the better your HRV. And that's the graph that we have here. Now, remember, because the client is not engaged, at this time I was not engaged in practicing, this is my baseline recording, you're going to see some counter beats here. And that's because my breath wasn't too ideal. I was stressed out, I was tired, I was not sleeping much. And so that's what it looks like. Now, if you don't fully understand the pulse wave, because it takes some time to get familiar with it, then you can scroll down and we're going to look at some specific numbers and graphs that will help you understand it. Okay. Now you see a lot of numbers here, like the RR mean, the median, the mode, the variance, occurred, skew. Don't worry about those. We're going to worry about 2 or 3 essential things here as it pertains to these graphs. The ones we're going to look at is the SDNN, which is the standard deviation of the normal to normal or the standard deviation of the RR series. Remember, SDNN, SDPP, SDRR mean exactly the same thing, right? And that's what we're going to look at. And the other elements we're going to be concerned with is the RMSSD. The RMSSD is a measurement of parasympathetic tone, parasympathetic strength. When we're measuring somebody at rest, not during HRV training, at rest, we're going to be looking at this number, the RMSSD, because again, it's a measurement of your parasympathetic strength, your rest and digest. You don't want too much parasympathetic, but you want some degree of parasympathetic tone, to have endurance, resilience, and optimal self-regulation. And then we're going to be worried with the maximum heart rate and the minimum heart rate. Because all those, the HR max and min, the RMSSD and SDNN, are tightly related to the physiology of heart rate variability, and those are the elements that will influence the EEG. So let's talk about each and every one of those first, and then we'll go into the spectral display. Again, the SDNN is just a statistical measure. SD stands for standard deviation. It's the standard deviation of the normal to normal, and it's measured in milliseconds. Why? Because remember that the time that elapses between one heartbeat and the other one is in milliseconds. Therefore, this number is in milliseconds, is the statistical averaging and the standard deviation, meaning, is this heart strong or not strong? That's essentially what it means. That's all you need to know. That's all you need to be concerned with, and that's all you need to explain to your client. Don't get fancy. Don't get cute. Just explain it like that. And what it does, it takes, in this case, all the IBIs that took place during those 3.5 minutes, and then put it into the formula here. And mine at baseline was 98.87, which is actually very good. And this is my next point. You want, for people on average, 80 or higher is always better at rest, baseline, not during training. If you're measuring your client, they come to the office, you put the helmet on, you record for 2 minutes, 5 minutes, 10 minutes. The SDNN at rest is of great interest, and 80 or higher is what you're going to shoot for. 80 or higher is a good measurement of strength. Now, bear in mind, I told you that I was stressed. At the time I did this recording, I was moving houses, I was getting ready for my trip to South America, I was finishing reports, I had a lot of things to do, and packing and working is not fun. And even though I was stressed, my SDNN shows that I'm having good resilience. And that's the key point here. It doesn't mean that your client is not going to feel stressed and that everything's going to be like a Disney movie and, you know, life is going to be perfect and everything's like through rose-colored glasses. No, it means that you're building resilience, that you're building the endurance to be able to sustain the period of stress without getting sick and without this affecting your mental health and your physical health. Therefore, what I've been doing through physical exercise and training myself every day with heart rate variability biofeedback is to create that resilience, that protective layer or shield against the stress. Stress still going around me. I was still experiencing some stress. I was just not succumbing to it the way I would if I didn't have a healthy, robust SDNN. So SDNN is the measurement you want to take a look at. The RMSSD, again, 70 or higher is what you want to shoot for. The higher, the better. Now, is there a high number you shoot for? No, not for the, neither for the SDNN nor for the RMSSD. The reason is it changes from day to day. If you're coming down with a cold, if you are at sea level versus altitude, if you just got off a plane, if you didn't sleep well the night before, if you're tired from exercise, if you were just having a fight with your spouse, any of those and more reasons can influence this. So what you shoot for is the higher, the better. And again, that will change from time to time. If the individual exercises, if they don't exercise, are they overweight? Are they fit? Are they healthy? Are they not healthy? But in general terms, 70 for the RMSSD and the SDNN 80 or more is what you want to shoot for. And at rest, my SDNN is almost 100. My RMSSD is 75. Now, it is normally higher, but because I was undergoing stress, I had a bit of more sympathetic activation. Again, I have the resilient factor. It's not that I'm not experiencing stress, it's just that I'm not letting it get to me as much as before. Now, let's talk about then the heart rate, the heart rate, the minimum and the maximum. And this has to do with the mechanics of breathing itself. One of the elements, one of the objectives of heart rate variability biofeedback is to increase the difference between your maximum heart rate and your minimum heart rate. And this is mediated by the depth and the pace of your breath, which means the slower you breathe and the deeper you breathe to a point, the more you're going to enhance this process. Okay? And this is mediated by the parasympathetic branch. So the way it happens is you breathe in, and as you inhale, you're going to speed up your heart rate. So your heart rate is going to speed up. Okay, and you can try it right now. As I'm talking, you can feel your pulse and take a couple of deep breaths going in, and you're going to see your heart speeding up. As you breathe out, as you exhale, the heart rate slows down. Okay, and what we're measuring here is at the end of the inhale, your heart rate, and at the end of your exhale, the heart rate. As an example, again, I'm breathing now, and I'm inhaling. I finish inhaling this, and I get to 70 beats per minute. And then I'm breathing out, breathing out, and this is 65. 70 maximum, 65 minimum. It's a difference of 5 beats per minute. 5 beats per minute or less is the sign of an unhealthy cardiovascular system. Again, you need to refer that client to the doctor. What you're going to shoot for in terms of the difference between the maximum heart rate and the minimum heart rate is at least 10 beats per minute or more. 10 or more. That means that if I'm breathing in and I did 70, breathing out, I want to reach 60 or less. And again, this depends on the client's health, their fitness level, where they live, if they have any medical conditions or not. You have to take all those elements, if they're taking medication or not. All those things you have to take into account. Luckily, I'm a very healthy person. I don't have any illnesses right now. I'm not taking any medication. I exercise a lot. I try to eat as well as I can. And so my numbers reflect that. Okay. I went to the doctor a few years ago to get a medical checkup, and he took my baseline heart rate, and my baseline heart rate was like 52 beats per minute. Now, 52 beats per minute on somebody who doesn't exercise, again, send them to the doctor. In my case, I do a lot of exercise. I started running through the pandemic. So I was running 10, 15K every day. And that's how I got the endurance. So my baseline heart rate was very low, but the doctor was very concerned. And he says, I want you to go get an EKG. I said, okay, I just want you to know I run every day. I run 15Ks. And he said, no, just regardless, go get an EKG. He was really worried that my baseline heart rate was very low. And I told him, I also do biofeedback. And he was like, what's that? So I explained to him. Regardless, he sent me to get an EKG. Thankfully, the EKG was healthy. So you have to take all these elements into account. And what you do to optimize and maximize the difference between the maximum heart rate and the minimum heart rate is breath work. The only non-invasive way in which you're going to enhance heart rate variability is through breathing. Is the only non-invasive way in which you can enhance and influence heart rate variability. Well, I shouldn't say that. The other one is exercise, but for emotional, cognitive, psychological, psychophysiological purposes is breath work. Exercise will strengthen it from the cardiovascular resistance perspective. That's why athletes have good HRV because they train for it, but their HRV for their psychological strength sometimes is not the best. And what do? Well, you can do it. You can enhance it and train it through biofeedback. So I'm hoping I'm making sense and I'm going slow enough. If there's any questions, we can revisit this at the end. For now, let's remember that we're concerned with the SDNN, the higher the better, the RMSSD, the higher the better, and the maximum heart rate versus the minimum heart rate, the higher the better. Now, again, these numbers are going to be somewhat different when we're training versus when we are at rest. And that takes us to the spectral display. So the other element that you want to be concerned with and know as a clinician, dominate as a clinician, so you can explain it to your clients as succinctly as possible, is the spectral display. And the spectral display is a frequency domain, this is a time domain, and this is frequency domain units, or rather graphs. And we're going to be concerned with the very low frequency, the VLF, it stands for very low frequency, the LF, which stands for low frequency, and HF, which is the high frequency. Okay, and they're going to be reflected here on the graph to the right, which is the spectral display. What is this the result of? The result of the person's breath work, whether they have trained or not, and whether they can breathe in a coherent, organized way. Now, if you notice here, there's a red dotted line, and that's the very low frequency zone, which is the equivalent to your sympathetic branch. So any activity in this zone right here, the very low frequency, is your sympathetic branch. You have the low frequency between the red dotted line and the blue dotted line, and that's your autonomic balance. Very low frequency sympathetic, low frequency autonomic balance, and then we have the high frequency between the blue and the green, and that's your parasympathetic. Okay, so sympathetic, autonomic balance, parasympathetic. Now, we're going to talk about autonomic balance versus parasympathetic, because this spectral display will have to look in two very different ways, excuse me, depending on whether we are training, we're measuring and recording as we're training somebody, or we're doing it at rest. Okay, now when we are recording a baseline, that is, you put on the helmet because the client comes for the very first time, or you want to do periodic recordings to see how they're doing, What you want to look for is for more activity in the high frequency spectrum, the high frequency absolute relative power and their percentage. So at rest, you have, or you want to see more activity in the HF, which is the RMSSD. It's reflective of parasympathetic tone. And that means that you have trained the person to get that endurance. When you are training somebody, you're recording somebody while they're doing coherent breathing, then you want the low frequency percentage to be higher than the other two. High frequency at rest, low frequency while training. To help you understand this better, let's use this analogy. When you go to the gym, you train, you do cardio, you do your weightlifting, right? You work very hard. But when it comes time to measure the progress, your trainer or your doctor is going to measure you at rest. They're going to take your heart rate. They're going to, take measurements of your muscles, your body mass index. And if you have been working very hard, if you have been eating well, it will show. And that's the low frequency percentage in the HRV spectrum. Sorry, the high frequency at rest. It shows that you have been working hard, you have been eating well, you have been sleeping well, everything shows here. So that's what we want to see. Now, the low frequency is when you're actually going to the gym. And there, you take your Polar watch, your Fitbit, your Apple Watch, whatever you use to monitor your heart rate and your VO2 max and all those fancy measurements. It's when you are at the gym or running outside or hanging out with friends, exercising, whatever it is you do for fitness. So the low frequency is while we're training, and the HF is the reflection of that training, which means that you're teaching heart rate variability to a client, you send them home with homework to do breath work. Every time you quiz them at the beginning of the session, you're going to be able to see if they're practicing or not. And these numbers don't lie. If they're doing their work, it will show. If they're not doing their work, it will not show. It's just that simple. So that's what we want to look at. Now, there's a caveat here. The challenge is once you have trained somebody to do breath work, they will not revert to breathing the way they used to. They normally do. What do I mean by that? If you see here, this is my resting measurement, but my low frequency is higher, and that is because as I had the helmet connected, I was engaged in purposeful breathing. When you're doing baseline testing, you should not have the client breathing like they do when they're training. You should ask them to breathe like they normally do. But now that they've learned to breathe correctly, that's what they're going to do. So what you want to do to distract them is have them watch a video or maybe talk to you a little bit, something that would distract them and won't activate them much. That way you can have a measurement of the high frequency percentage. But it's very hard for me. It's very hard to sit here and just pretend like I'm breathing like I normally would, because it's very counterintuitive. I have been training HRV for, 10 plus years now. That breathing in a way different from the coherent breathing is very strange to me. Nonetheless, that's what you want. Therefore, have the client, maybe read a book, not out loud, but read a book or watch a video, a neutral video that won't activate them, that won't trigger them, and then you can have the high frequency measurement. Important thing to remember, high frequency is when we are at rest, low frequency when we are training. And this will be correlated to the SDNN, the RMSSD, and the heart rate minimum and maximum. What does it mean? The higher the SDNN, the slower and the deeper you're breathing when you're training, and the more endurance you're going to build, and the more robust your RR series is going to look like. So that's what we have. As I scroll down, you're going to see these pointer plots. This we're not going to go over because you don't really need to know it. It's going to complicate things more. So if I start explaining this in detail, I'm going to get more confused, and I'm going to confuse you even more, because this is just a fancy way of plotting the data. It's mostly used for research. Your client in the end won't care about this. They just want to know how you're going to get them to feel better. And to do that, you explain the spectral display. You explain to them what very low frequency means, what low frequency means, and why, and what high frequency means. And then you explain to them the SDNN, the RMSSD, the heart rate minimum and maximum, and the RR series. That's all you need to know from this end. Now I'm going to stop sharing my screen, and I'm going to share it now. I'm going to share the summary report. Now here you have the mean or average heart rate. So see, mine was 58.46. And if every time I go to the doctor and they see this, they freak out. Even though I tell them, look, I exercise and I do heart rate variability biofeedback every single day, they still get freaked out. And this is high at the time because, as I explained, I was stressed. Normally it goes down to 54, 53. So, even though I'm 47 years of age, I'm not getting any younger. I'm no spring chicken. My heart rate is still healthy. And this is the average, the minimum heart rate, and the maximum heart rate. So you can see my maximum heart rate when I finish inhaling is 71.43, 72 beats per minute. And when I stop exhaling, it's about 48 beats per minute. This is a very nice difference here. Okay. So the stress index 26.17 is a score. The lower, the better. The lower your stress index, the better. It means you're self-regulated, you're relaxed, you're chill. And here you have the RMSSD and the SDNN. So if you don't want to toggle back and forth, this refreshes this info for you, and then you can refresh it for the client. To the right, you have a pie chart, if you can call it that, where it shows your sympathetic to parasympathetic ratio. And as you can see, even though my SDNN is quite strong and my RMSSD is quite strong, I had more sympathetic activation. I was stressed. I was experiencing stress. I was not feeling as stressed, but there was stress going around. Psychological stress and physical stress. Now, for practical purposes, when you are measuring and assessing at rest, your PNS, your parasympathetic nervous system, is going to be higher. So roughly, I would say maybe 40 to 60% higher or more than your sympathetic nervous system. When you are training and you want the low frequency autonomic balance, then this is about 50-50. At rest, you want the parasympathetic to be higher, and during training, about 50-50. And that's all you need to know. So we're not going to overcomplicate things here. As we scroll down, you get a plotting of the data. So the dot indicates my state, which in this case is the state of your client, and I'm at excellent. I'm not at overload. I'm not weak. I'm excellent, which means that fitness and nutrition and heart rate variability biofeedback and neurofeedback have paid off for me. Okay, it's made me a healthier individual, and therefore it's very important. Why? Because I have genetic predisposition to cancer. I have genetic predisposition to glaucoma. I have genetic predisposition from my grandparents to cardiovascular disease, cancer, diabetes. I mean, you name it. Both my paternal and maternal grandparents were quite ill with cancer. Two of them died of cancer. One of them died of diabetes. My maternal grandmother almost made it to 100, and the only thing she had was glaucoma to the end of her life. But it means I have the genetic predisposition. It's in my best interest to stay as healthy as I can. So this is excellent, which is good. This is where you want to see your client. And if I sound like I'm bragging, I apologize. That's by no means my intent here. Now, This is just another distribution for this. So this is one way of seeing it. And you probably will encounter clients who, do not understand this. Well, then you can have this. So the histogram essentially shows three colors. You can see a lighter bluish here, which is the excellent. And that's where most of my RR distribution is, as you can see. And you can now see here, this is leaning towards the parasympathetic branch. This is the normal here in the grayish, and then this pink or salmon is the poor. And as you can see, again, my heart rate variability distribution is within excellent, which is what you see here. If it was weak, if it were in the weak section, then you would have all these bars up here. And if they're normal or, poor or overload, they're somewhere around here. So that's what we end up getting. Now, this will show you 5 stages. And again, everything you see here, think of EEG, QEEG. Starts with the raw EEG, which is in this case, the RR series. And when we go into the QEEG with the spectral displays and the coherence maps and connectivity and topographic, this is the equivalent to QEEG in HRV. But what you need to look at, what you need to understand is your raw data. Okay, you need to de-artifact the raw data, look at the make sure there's no memorex in that raw data, and then look at the graphs. And this shows you 5 stages. Homeostasis was my current condition at the time. Again, even though I'm stressed out, even though I was undergoing a lot of crap, I was able to hold my ground. Then you go into alarm, and you can see a description for that here. So you are in a stable condition with 0 to little stress. That was not the case, but at least my body was expressing it that way. And it gives you some recommendations. Alarm, resistance, exhaustion, and burnout. So you can actually see that, and it will probably correlate very well with your EEG. You will see either a slowly dominated EEG with lots of delta frequencies and theta frequencies. You might pick up stage 2 sleep patterns in the eyes open EEG, or early in the eyes closed EEG recording. You may pick up insula activity, like with transients over T78, F7, T78, F7, F8. You will pick up beta spindles, maybe some excess gamma. So the activity that you will see here will correlate very nicely with what you end up seeing in the EEG. And based on these findings, you're going to make recommendations. The other feature that I really like about this is that it gives you a depression index and an anxiety index. Now, word of caution here, this should be taken with a grain of salt. Do not take it at face value, because there's more to anxiety and depression that meets the eye. However, you can discern their emotional state to some degree based on their heart rate variability activity, the activity of the heart and the activity of the brain. Now, it shows that my score is mildly depressed. Yes, I was feeling, I would say depressed. I wouldn't say depressed was the word to describe, but I was feeling somewhat tired or maybe defeated. I was just undergoing a lot of things, and I didn't feel at the time that I could cope. Now, again, I'm expressing that verbally and emotionally, yet physiologically, I'm quite protected from it. And I guess this mildly depressed, in a way, helped me a little bit, because had I not been that way, I would not be aware of everything I needed to do. And it showed my score as anxious, because yes, I was anxious. I was thinking that I was not going to be able to get the move completed, help my wife with the move, get my presentations ready for my workshops here in South America, be able to get the future workshops that I have ready ahead of time. There was a lot going on. And it reflects in my anxiety score. And then you have 3 levels: normal, mildly depressed, and then normal, mildly anxious, and actions, with some recommendations. Now, these recommendations are more for the user in mind. As a clinician, of course, with all your expertise and your experience and your education and your credentials, you're going to be able to provide way more than this. But at least it provides you with a foundation, especially if the client asks for the reports that this prints. So I think I did okay with time. I normally get overzealous and carried away, and people have to stop me. So this is in a nutshell. And thank you for your attention. I'm going to open up the floor for questions now.